Hello guys, this is Sirup Dotto from Expert Mathematica. Today I will be discussing a question from CSIR NET December 2023. Question number 25 and question ID 704072. This question is from linear algebra and question is from part C. So it has 4.75 marks and we have to check each and every option individually. So given that T is a linear transformation from 5-dimensional real vector space to 5-dimensional real vector space, and given three vectors which spans its null space. So we have to check its options. Given first option, its rank of T equals 2. So to check this, first of all we have to re-verify these vectors are linearly dependent or linearly independent. So let's check this. So we will take three rows. Given vectors are 1, -1, 2, 4, 0, 4, 6, 1, 6, 0, and 5, 5, 3, 9, 0. And if we take row operation is R2 minus 4R1 and R3 minus 5R1, we'll get 1 minus 1 2 4 0. This doesn't change. We have 10 0 10 minus 7 minus 10 0 and 0 10 minus 7 minus 11 0. Now this row and this row is linearly independent because of these two entries. This is sorry guys, this is minus 10. Okay, minus 10 for this entry. This two rows becomes linearly independent. So dimension of curve T equals 3 because 3 vectors spans it, and dimension of 5-dimensional real vector under real field is 5. So dimension of range of T or rank of T by Sylvester's law will be dimension of vector space minus dimension of its kernel, which is equal 5 minus 3 is 2. So option 1 is true. Now given that second option is given, suppose that for every vector V there exists n such that T to the power n V is 0. For every vector V there exists n such that T to the power n of V is 0, then T square must be 0. And same things is given for every vector V in option 3 there exists n such that T to the power n V is 0, then T cube must be 0. We will check these two options in similar manner. So given that for all V in R to the power 5 there exists n, so we will take the least positive integer n such that T to the power n of V is 0. So this is for all vector V there exists n such that T to the power n V is 0. So dimension of curve of T to the power n must be 5. Now since dimension of vector space is 5, and let me give you one inequality. We claim that null space of T subset null space of T square subset null space T to the power n null space of T to the power n plus 1 and so on. This subset inequality will continue up to this is true. This is true na. You can easily check this. If V belongs to null space of t to the power n plus 1, then sorry, t to the power n, let me erase this. If V belongs to null space of t to the power n, then t to the power n of V is 0. If we apply t on both sides, we get t to the power 1, t to the power n plus 1 of V is t of 0. Since this is linear transformation, so t of 0 is 0. This implies V belongs to t to null space of t to the power n plus 1. So this subspace inequality will continue. Okay. Now, since this subspace inequality will continue, so dimension of null of t is less than equals to dimension of null of t square less than equals to dimension of null of t cube less than equals to less than equals to dimension of null of t to the power n. This is less than equals to dimension of null of t to the power n plus 1, and this inequality will continue. Now my claim is, since dimension of kernel of t to the power n is 5, so it's, and we have dimension of vector space is 5, so it is maximum dimension. So dimension of kernel of t to the power n plus 1 will not increase. So it will be equal na dimension of kernel of t to the power n plus 1. So our claim is, now my claim is, if null space of t to the power n equals null space of t to the power n plus 1, then null space of t to the power n equals null space of t to the power n plus r, where r is greater than equals to 1. R is 1, 2, 3, and all will be equal. So let's prove this. Proof is easy, and this is easy part na. Null space of t to the power n is subspace of null space of t to the power n plus 1. So let's prove its converse. Easy. Let's prove its converse. So let V belongs to null space of t to the power n plus r. Okay. So this implies t to the power n plus r of V equals 0. This implies t to the power n plus 1, t to the power r minus 1, this is r minus 1 of V will be 0. This implies t to the power r minus 1 of V equals belongs to kernel of t to the power n plus 1, and sorry guys, this is not kernel, this is null space of t to the power n plus 1, and we previously have t to the power n plus 1, null space of t to the power n plus 1 equals null space of t to the power n. So now this equals null space of t to the power n. So see, t to the power r minus 1 of V belongs to null space of t to the power n. So this implies t to the power n of t to the power r minus 1 of V will be 0. This implies t to the power n plus r minus 1 of V equals 0, and this implies V belongs to kernel of t to the power n plus, sorry, this is null space of t to the power r minus 1. We previously have V belongs to null space of t to the power n plus r, and we now have V belongs to null space of t to the power r minus 1. So after r step, continuing this manner, after r steps, we will have V belongs to null space of t to the power n. So we have this inequality, equality, null space of t to the power n equals null space of t to the power n plus r for r greater than equals to 1, when null space of t to the power n when null space of t to the power n equals null space of t to the power n plus 1. Now, why I prove this? We need this proof. We previously had dimension of null space, dimension of null space. Sorry, dimension of null of t. That sorry guys, that will be dimension of cut t. Sorry, dimension of null of t. Okay, sorry guys, this there will be null of t. All will be null of t. Sorry guys, this will be null of t, and these things are similar. Okay, so what we have, dimension of null of t to the power n. We previously have this is equals 5, and since maximum dimension is 5, so this will be equal dimension of null of t to the power n plus 1. Okay, so we have this inequality, dimension of null of t is less than equals to dimension of null of t square less than equals to dimension of null of t cube, and so on up to dimension of null of t to the power n, and after this equals dimension of null of t to the power n plus 1. Okay, and so on. So what is happening now? So we have dimension of null space of t is 3. Now we claim that we previously claimed that if the equality occurs in some cases, then all are equal after this. Okay, so up to equality, we have previous inequality. So if dimension of null of t, so what I am trying to say is dimension of null of t must be strictly less than equals to dimension of null of t square, strictly less than equals to dimension of null of t cube, and this strict inequality goes up to dimension of null of t to the power n, and we have equality after this. If we have equality in previous one of these, then all must be equal after all of this. So we have dimension of null of t is 3. So for dimension of null of t square, we have two choices, either 4 or 5, since this is 5-dimensional vector space. And suppose dimension of null space of t square is 5, then all are equal. Then dimension of null of t cube will be 5, and all will be equal. If dimension of null of t square is 4, then dimension of null of t cube must be 5, and this equals all of its dimension. Dimension of null of t to the power 4, dimension of null of t to the power 5, all must be 5. So if dimension of null of t square is 4, this may be a case. For this case, dimension and for this case dimension null of t cube must be 5, and for this case dimension of null of t cube is also 5. So t cube, so for all v belongs to r to the power 5, t cube of v must be 0. Okay, since this is 5 dimensional vector space and dimension of null of t cube is 5, and dimension of null of t square may be 4. So option 2 is given t square must be 0. This will not true. T square may be 0. If dimension of null of t square is 5, then t square is 0. If dimension of null of t square is 4, then t square is non-zero. So option 2 is incorrect and option 3 is correct. Now we have to check this vector -2 -8 3 2 0 is contained in the null space of T, and this is easy to check. So if that vector contained in null space, we have null space 3 vectors. So so the span of this vector 1 -1 2 4 0 and C2 4 6 1 6 0 and C3 5 5 3 9 0. This spans the null space of T. So these 3 vectors spans the null space of T if that vector given -2 -8 3 2 0. Let me recheck this. -2 -8 3 2 0. So if that vector belongs to the null space of T, so span of this will equals -2 -8 3 2 0. So let's take the augmented matrix portion and let's solve this. We have 1 -1 2 4 0 4 6 1 6 0 5 5 3 9 0 and augmented portion is -2 -8 3 2 0. So let's do some row operation. If we take R2 plus R1, R3 minus 2R1 and R4 minus 4R1, this is plus R2 plus R. So we have this matrix 1 2 5 minus 2. We have 0 10 10 minus 10 0 minus 7 minus 7 7 0 minus 10 minus 11 10 and 0 0. Now let's take 1 by 10 R2 and minus 1 by 7 R3. We will have 1 4 5 minus 2 augmented portion, which equals 0 1 1 minus 1 0 1 1 minus 1 0 minus 10 minus 11 10 and 0 0 0 0. So if we take R3 minus R2, we will get this 0, and if we shift all if we shift R4 and R3, we will finally get 1 4 5 minus 2 augmented portion 0 1 1 minus 1 0 minus 10 minus 11 10 0 0 0 0 0 0 0 0. Okay. So let's do another operation on this. We will get R1 minus 4R2 and R3 plus 10R2. So after this operation we will get 1 0 1 plus 2 and 0 1 1 minus 1 0 0 minus 1 0 0 0 0 0 0 0 0 0. If we take minus of R3 we will get this, and if we take R2 minus R3 and R1 minus R3 we will get 1 0 0 which equals to 0 1 0 which is equals minus 1 and 0 0 1 0 and 0 0 0 0 0 0 0 0. So if we take C1 is 2, C2 is minus 1 and C3 is 0, where we have this C1 is 2, C2 is minus 1, C3 is 0, we will get this vector. So minus that vector given is contained in the null space of T. So option 1, 3 and 4 is correct. So you will get 4.75 marks very easily. So you guys, if you guys like this video, please don't forget to hit the like and subscribe button, and please support my channel. Thank you guys.